Hello, and welcome to Differential Equations. This is lecture 27, Putzer's algorithm. Last time we discussed the exponential of a matrix. This time we're going to talk about another way of finding the exponential of a matrix. Okay, so let's recall where we are. If A is an n by n matrix with constant entries, then e to the a times t is the fundamental solution matrix of the equation dv by dt is equal to a times v, which is equal to the n by n identity matrix at t equal to 0. Also, e to the a times t is equal to identity plus a times t plus a squared t squared over 2 factorial, and so on, right? In sigma notation, this is the sum k goes from 0 to infinity of a to the k, t to the k over k factorial. And then also, if v1 through vn is a complete set of eigenvectors for a matrix A with A times Vj equal to lambda j Vj, and U is the matrix whose columns are precisely these eigenvectors, then A is equal to U times the diagonal matrix with these eigenvalues on the diagonal times U inverse, and e to the a times t is equal to U times the diagonal matrix with e to the lambda 1t, e to the lambda 2t, and so on the diagonal times U inverse, right? So on the one hand, you can't compute the exponential as the fundamental solution matrix. That's not the approach we mostly want to take, because instead we want to use the exponential to find the fundamental solution matrix, right? We want to use the exponential to solve this equation. On the other hand, you can compute the exponential using this series, although that's difficult because most of the time it's really hard to know what the terms of a to the k are, what the individual entries in that matrix are equal to. A third approach which works great if you can find a complete set of eigenvectors is you can diagonalize A, and then it's very quick to compute the exponential, right? So that's where we're at right now. This third approach is great, but what can we do? if A doesn't have a complete set of eigenvectors. Well, today we'll see an approach that works even then, and it doesn't require for us to compute any eigenvectors. Only eigenvalues. This method takes advantage of the following fact, known as the Cayley-Hamilton theorem. Right, so here Cayley is one of the mathematicians who developed the theory of matrices in linear algebra. Hamilton is the mathematician who came up with the quaternions. If A is an n by n matrix, and lambda 1 through lambda n are its eigenvalues, repeated with their multiplicities, and we define B0 to be the identity, B1 to be A minus lambda 1 times the identity, B2 to be A minus lambda 2 times the identity times B1, and so on. Bn minus 1 would be A minus lambda n minus 1 times the identity times Bn minus 2. And then finally, Bn, A minus lambda n times the identity times Bn minus 1, right? So that means it's A minus lambda n times the identity times A minus lambda n minus 1 times the identity, and so on until you get to A minus lambda 1 times the identity. Then Bn is the zero matrix, right? So that's what the Cayley-Hamilton theorem says, that if you take the eigenvalues of a matrix repeated with multiplicity, so an n by n matrix, you always have exactly n, and then you form these matrices, A minus eigenvalue times the identity, and multiply them all together, then you'll get 0. Okay, so that's what's behind making this algorithm work. So this is Putzer's method for computing the exponential of a matrix. Okay. So this is named after E.J. Putzer, who published this algorithm in 1966. So here's what you do. First, you find lambda 1 through lambda n, and B0 to Bn minus 1. Next, you have to solve a few ODEs, but very simple ODEs. So first you find R1, satisfying R1 prime of t is lambda 1 R1, with initial condition R1 of 0 is equal to 1. Then you find R2 of t, satisfying R2 prime of t is lambda 2 R2 plus R1 with initial condition R2 of 0, 0, right? And so on until you find Rn of t, satisfying Rn prime of t is lambda n Rn plus Rn minus 1 with initial condition 0 at 0. Right, and then finally, once you've found all of those, the exponential we're looking for is R1 of t times the matrix B0 plus R2 of t times the matrix B1 plus dot 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 Rn of t times the matrix Bn minus 1. Right, so in sigma notation, the sum from k goes to 0 to n minus 1 of r to the k plus 1 of t bk. Okay, so why does this work? So let's take n equal to 3 for simplicity, but the general case is the same. You just put a lot more dot dot dots. So let's define phi of t to be the sum k goes from 1 to 2 of r k plus 1 of t bk. Right, so this is the thing that's supposed to be the exponential. So to show that it is equal to the exponential, we'll show that on the one hand, phi prime of t is equal to a times phi of t. And on the other hand, phi of 0 is equal to the identity matrix, right? And hence, because this means that it is the fundamental solution matrix for the equation dv dt equals AV with initial condition and it's equal to identity at t equal to 0, that will show that it is indeed the exponential. Okay, so how do we show this? Well, first of all, if you evaluated 0, right, well, all of these functions have initial condition 0 except for R1. So if you evaluated 0 in this sum, the only one that survives is R1. So we end up with R1 of 0 times B0, right? But remember, B0 is the identity matrix, and R1 of 0 is 1, so this is just the identity. Okay. Next, let's compute the derivative. So the derivative in a sigma notation, this would just be the sum k goes from 1 to 0 from 0 to 2 of rk plus 1 prime of t times bk, right? So that would be from the differential equations that each of these r's satisfy, we see that this would be lambda 1 r1 times b0 plus lambda 2 r2 plus r1 times b1 plus lambda 3 r3 plus r2 times b2. Okay. Now, recalling what how we defined these matrices b1, b2, and so on, notice that I can write lambda 1 b0 as a times b0 minus b1. Lambda 2 b1 is equal to a b1 minus b2, and lambda 3 b2 is equal to a b2, right? So all I'm doing is solving here right, for lambda 1 b0. Remember, b0 is the identity. So here, if I solve for lambda 1 times the identity, I get a minus b1. If I solve for lambda 2 times b1, I get b2 minus a times b1, and so on. So that means I can rewrite this as R1 times a b naught minus b1 plus R2 times a b1 minus b2 plus R1 b1 plus R3 a b2 plus R2 b2. Okay, and now that's equal to R1 a b naught minus R1 b1 plus R2 a b1 minus R2 b2 plus R1 b1 plus R3 a b2 plus R2 b2, right? Now notice that I can cancel this one with this one and this one with this one. And so the terms that are left all have an a that I could factor out, and then I end up with R1 b naught plus R2 b1 plus R3 b2. And that's exactly a times v of t, just like we wanted. Okay, so that's why Putzer's algorithm works. So now we're going to do some examples. I will do all of the exponentials we computed last class. I'll now compute them using Putzer's algorithm, so you can compare the two methods. So let's start with a diagonal matrix. Here the eigenvalues are obviously 2 and 3. So that means that B0 is going to be the identity. B1 is a minus 2 times I, right? So that would be 0, 0, 0, 1. And then B2, I don't need to compute. It's just equal to 0 by the Cayley-Hamilton theorem. So those are the B matrices. Now I have to find the coefficient functions R1 and R2. So here, R1 prime is equal to 2R1 with R1 of 0 equal to 1. So that's really quick to solve. That's e to the 2t. Right? Whereas R2 satisfies R2 prime is equal to 3R2 plus e to the 2t, and R2 of 0 equal to 0. Right? So this was very quick to solve because it's a homogeneous first order equation. This is non-homogeneous, right? The associated homogeneous would just be these terms. So we solve this in the usual way. We find a particular solution, and then we add the general solution to the associated homogeneous equation, and then we find the arbitrary constant by using this initial condition, right? So this is still a very easy equation. The solution is e to the 3t minus e to the 2t. So once we've found those, then we can write down the exponential. So R1 B0 plus R2 B1. So that would be e to the 2t times the identity matrix plus e to the 3t minus e to the 2t times B1, right, which we computed right here. So that means we have e to the 2t on the diagonal plus 0, 0, 0, e to the 3t minus e to the 2t. And then when you add those together, you get e to the 2t and e to the 3t on the diagonal, which is exactly what we expected from here. Right? Next, let's compute the exponential of the matrix 0, 1, 1, 0. Okay, so last time we computed the eigenvalues. They are -1 and 1. So that means that B0 is the identity and B1 is A plus I. Notice that you don't have to put the eigenvalues in increasing order, as I like to do. This algorithm will work just fine with the eigenvalues in whatever order you like, as long as you make use of that order, both when you're finding the B matrices and when you're finding the coefficient functions R. So here, A plus the identity would be 1, 1, 1, 1. And then B2, I don't need to compute. It's 0 by Cayley-Hamilton. Coefficient functions, R1 prime would be equal to minus R1. R1 of 0 is equal to 1. So this has solution e to the minus t. And then R2 prime would be equal to R2 plus R1. R2 of 0 is equal to 0. So again, we find this by finding a particular solution and then adding the general solution of the associated homogeneous. In this case, you can work out that it's 1/2 of e to the t minus e to the minus t. So that means that the exponential, right, R1 B0 plus R2 B1 would be e to the minus t times the identity plus 1/2 e to the t minus e to the minus t times B1. All right, so that's to say e to the minus t on the diagonal for this first term. And then the second term just has 1/2 e to the t minus e to the minus t in all 4 spots. And so if I add these together, it's just going to shift the terms on the diagonal, become 1/2 e to the t plus e to the minus t. And the off-diagonal terms remain 1/2 e to the t minus e to the minus t. Right? Just like we got last time. Okay, next. Let's look at the matrix 0, minus 1, 1, 0. The eigenvalues of this matrix, right? The characteristic polynomial is quick to compute. You get lambda squared plus 1. So that means that the eigenvalues are going to be minus I and I. So that means that B0 is the identity. B1 is equal to A plus I times the identity. So that would be I minus 1, 1, I. And then B2, you don't need to compute. It's just 0 by the Cayley-Hamilton theorem. Our first coefficient function, R1 prime, is equal to minus I R1 with initial condition R1 of 0 is equal to 1. So that gives R1 of t equals e to the minus it. The second coefficient function, R2 prime, should be equal to I R2 plus R1. And it satisfies the initial condition R2 at 0 is equal to 0, right? Which here means that we should take minus I over 2 times e to the it minus e to the minus it, right? And then notice that that's just the imaginary part of e to the it, which is sine of t. So then if we write down what that means for the exponential, we get that e to the at is equal to R1 B0 plus R2 B1. So e to the minus it times the identity matrix plus sine of t. times b1. So that means I have e to the minus it, 0, 0, e to the minus it, then plus I times sine of t minus sine t, I sine t. Okay, and now remember that e to the minus it by Euler's formula, that's equal to cosine t minus I sine t. So minus I sine t in this term and this term is exactly going to cancel these I sine t on diagonal, and so we just end up with cosine t sine t minus sine t cosine t, just like we found last time. Something that happens here that happens a lot in Putzer's algorithm is that we had to work with complex numbers as intermediate steps in our computation, but we ended up with a matrix that only has real numbers. So note that this is a general fact. If A has only real entries, then e to the at has only real entries. We know that because, for example, we could compute it using the Taylor series method. And in that Taylor series method, you're doing a series of matrices, but all of them have real entries because they're just powers of A. So we're going to end up with only real entries, even if we use complex numbers to find them. Right. Of course, if you start out with a matrix that has complex entries, then the exponential will end up with complex entries in general. Okay, let's do another example. Suppose you started with A given by 0, 1, 0, 0. This is an example of a deficient matrix. The eigenvalues are 0 with multiplicity 2, and 0 only has geometric multiplicity equal to 1. Right? But for Putzer's method, you need to repeat the eigenvalues with their multiplicity. So here, because 0 has multiplicity 2, I repeat it twice. So B0 would be the identity matrix, and B1 would be A minus 0 times the identity, so that's just A. So 0, 1, 0, 0. B2 would just be the zero matrix by Cayley-Hamilton. Coefficient matrix, here R1 prime of t should be equal to 0. 0 times R1, and that's just 0. With initial condition that it's equal to 1 at 0. So derivative equal to 0 means that it's a constant. If the constant at time 0 is equal to 1, that means that the function is just identically equal to 1. Our second coefficient function would be 0 R2 plus R1, right? R2 of 0 is equal to 0. So that means that, right, this is just 0. So the R2 prime is equal to 1. So that means that it's equal to a plus b times t. But if we want it to be not b times t, just t. So it's a plus t is the general solution, but you want it to be 0 at 0. That means that R2 of t is just a function t. Right? And then with those coefficient functions computed, we can just write down the exponential. Right? So this would be 1 times b naught, so that's the identity matrix, plus t times b1. And so that would just be 1t, 0, 1. Just like we found last time using the power series. Okay. Next, let's consider the matrix A given by minus 4, minus 3, 2, 3. The eigenvalues are minus 3 and 2. So B0 is the identity matrix. B1 would be A plus 3 times the identity. So that would be minus 1, minus 3, 2, 6. And then B2 would be 0 by Cayley Hamilton. Here R1 prime is equal to minus 3R1 with initial condition equal to 1 at 0. So that means that R1 is e to the minus 3t. R2 satisfies that R2 prime is equal to 2R2 plus e to the minus 3t. R2 of 0 is 0. Right? So again, we find this by finding a particular solution for which we could just do undetermined coefficients and try a times e to the minus 3t. You plug this in to find that a would be minus 1/5. And then you add to that the general solution of the associated homogeneous equation. So that would be a multiple of e to the 2t. And then you use this initial condition to find what multiple of e to the 2t you should take. And in this case, you end up with 1/5 times e to the 2t minus e to the minus 3t. Okay, and now that we have the coefficient functions, we can write down the exponential. This is R1 B0 plus R2 B1. So that's e to the minus 3t times the identity plus 1/5 e to the 2t minus e to the minus 3t times B1, right? So I end up with e to the minus 3t, 0, 0, e to the minus 3t, plus, okay, and then we have, well, let me keep this factored, 3t, and then I have minus 1, 2, minus 3, 6. And so altogether, that's minus 1/5 e to the 2t. And then I have minus 1/5 plus 1. So that's, with a minus sign. So that's 1/5 plus 1. So that's 6/5 e to the minus 3t. Then let's see, down here I just have 2/5 e to the 2t minus e to the minus 3t. And here I would just have minus 3/5 e to the 2t minus e to the minus 3t. And then here I have 6/5 e to the 2t. And then minus 6/5 plus 5/5 is minus 1/5 e to the minus 3t. Okay. So that's that one. Right. Next, let's do a 3×3 example. So suppose we're looking at the matrix 2, 3, minus 3, minus 3, minus 4, 3, minus 3, minus 3, 2. So here we've found the eigenvalues are minus 1 with multiplicity 2, and then 2, multiplicity 1. So B0 would be the identity matrix. B1 would be A plus the identity. So that would be 3, 3, minus 3, minus 3, minus 3, 3, minus 3, minus 3, 3. Right? Which I'm just going to point out is 3 times 1, 1, minus 1, minus 1, minus 1, 1, minus 1, minus 1, 1. Then B2 would be A plus the identity times B1, right, which is the same as A plus the identity squared, right? So that 3 squared gives us 9. And then this matrix, when we square it, we get 1. And then, right, then to find this entry, we do this times this, and we get 1. And similarly, to find this entry, we end up with -1, then -1, -1, 1, -1, -1, 1. So it's just 9 times the same matrix we had here. Right? And then we don't need to compute B3, but Cayley-Hamilton tells us that it's 0. Okay, so now our coefficient functions, R1 prime would be equal to minus R with initial condition 1, which makes it e to the minus t. R2 prime would be equal to minus R2 plus e to the minus t with initial condition 0. So you can compute that t e to the minus t solves that equation. And then R3 prime would be equal to 2 times R3 plus t e to the minus t with initial condition 0. And you can compute that the solution to this equation is 1/9 e to the 2t minus e to the minus t minus 1/3 t e to the minus t. Okay, so then the exponential is R1b0 plus R2b1 plus R3b2. So it's e to the minus t times the identity plus t times e to the minus t times b1 plus this whole thing, 1/9 e to the 2t minus e to the minus t minus 1/3 t e to the minus t times b2. So that looks like e to the minus t times the identity matrix and then I'm going to use that b1 is equal to 3 times this matrix, whereas b2 is 9 times the same matrix, to write this as 3 times t e to the minus t plus 9 times all of this, 1/9 e to the 2t minus e to the minus t minus 1/3 e t e to the minus t, right? All of that times this matrix, 1, 1, minus 1, minus 1, minus 1, 1, minus 1, minus 1, 1. Okay, so let's leave that as it is. But now let's work out what we get here. So this 9 times this minus 1/3 is minus 3 t e to the minus t, and we have 3 there, so this one will cancel with this one. And then this 9 cancels with that 9, and so here I just end up with e to the 2t minus e to the minus t times this matrix. Okay, so now let's go ahead and compute. So I end up with e to the 2t there, and then e to the 2t minus e to the minus t, and then e to the minus t minus e to the 2t. Then here I end up with e to the minus t minus e to the 2t. Then here, let's see, I have e to the minus t, and then I subtract this, so that gives me 2e to the minus t minus e to the 2t, and then e to the 2t minus e to the minus t, e to the minus t minus e to the 2t, e to the minus t minus e to the 2t, and then this is again e to the 2t. There you go, just like we got last time. Okay. Right, let's do then another example of a deficient matrix. You have 2, 1, 0, 2. So there's only one eigenvalue, but it has multiplicity 2. Here B0 is the identity, B1 is a minus 2 times I, so that's 0, 1, 0, 0. B2 is equal to 0 by Cayley-Hamilton. Our coefficient functions satisfy R1 prime is equal to 2 R1. R1 of 0 is 1, so that means R1 is just e to the 2t. R2 prime is equal to 2R2 plus e to the 2t. R2 of 0 is equal to 0. So then R2 of t, right, usual thing, you look for a particular solution, right? You would guess a multiple of e to the 2t, but that solves the homogeneous equation. So then you guess t e to the 2t, right? And it turns out that that solves, and it satisfies the initial condition. So that is the solution. And once you have the coefficient functions, you can compute the exponential, R1 B0, R2 B1. So that's e to the 2t times the identity plus t e to the 2t times B1. And so e to the 2t on the diagonal, t e to the 2t above the diagonal. Okay. Let's do one more example involving complex eigenvalues. So let's take A to be the matrix 3, 5, minus 1, minus 1. So the eigenvalues of this matrix are 1 plus I and 1 minus I. So if you, let's put them in the opposite order, although we could do it in either order. So that gives us B0 is the identity, B1 is equal to A minus 1 minus I times the identity. So that would be 2 plus I, and then this doesn't change, so 5, and then minus 1, and then minus 2 plus I. Right? B2 would be 0 by Cayley-Hamilton. Right? Our coefficient functions, so R1 prime would be equal to 1 minus I times R1 with R1 at time 0 equal to 1. So that means R1 of t would be e to the 1 minus I times t. R2 prime would be equal to 1 plus I times R2 plus R1, so e to the 1 minus I times t. R2 of 0 is equal to 0. Right? So again, we solve this the usual way. You use undetermined coefficients to find a particular solution. You guess a multiple of this one. You plug it in. You find that you need minus, I over 2 times this will work. And then you find the general solution of the homogeneous, add those together, and then put in the initial condition to work out that you should take minus I over 2 times e to the 1 plus I times t minus e to the 1 minus I times t. And if you use Euler's theorem, you can simplify that to e to the t times sine t. Okay, so that means that e to the at is going to be R1 B0 plus R2 B1. So that's e to the 1 minus I t times the identity plus e to the t sine t times B1. So that's e to the 1 minus I t times the identity matrix, and then e to the t sine t times 2 plus I, 5 minus 1 minus 2 plus I. So I could pull out a common factor of e to the t from both of these, right? And then let's see here, if I pull out the e to the t, I end up with e to the minus it times 1. So that would be e to the minus it. So that's cosine t minus I sine t, right? 0, 0, cosine t minus I sine t. And then if I pull out the e to the t as a common factor, then I end up with sine t times these. So that's 2 sine t plus I sine t minus sine t, 5 sine t minus 2 sine t plus I sine t. Right? So notice this minus I sine t cancels with that one. And this minus I sine t cancels with that one. And so altogether we get e to the t. And then we have cosine t plus 2 sine t. We have 5 sine t minus sine t, and then cosine t minus 2 sine t. Okay, and we'll stop there and pick it up next time.